Hello everyone, my name is Benedek Horváth, and today I would like to present you Modest 3, a success story to win children's heart for model-driven engineering. I was a bachelor and master student at the Budapest University of Technology and Economics. Inside the Critical Systems Research Group, there was a project called Modest 3, in which I was one of the core developers during my studies. Nowadays, I'm a PhD student at Johannes Kepler University at Linz and at Inquiry Labs Budapest. Critical Systems Research Group is a research group at the Budapest University of Technology and Economics. Its research areas are developing critical systems, verification and testing, and empirical system design. In 2014, the research group started a project called Modest 3 in order to demonstrate and show the capabilities and expertise of the research group in model-driven engineering and in formal verification. The Modest 3 stands for Model-Based Demonstrator for Smart and Safe Systems. It's a model railway track which consists of several sections and switches, and our goal was to prevent the train's collision on the track. The track consists of 31 segments, from which 24 are sections, and there are 7 switches. The switches are responsible for the directly connected sections, so the sections which are directly connected to this switch, and the neighboring sections are controlled by other switches. In order to supervise the track, the sections are communicating with each other to decide where the trains are moving, and in order to stop the trains before they would collide into each other. Let's have a look under the hood on the physical infrastructure. One of the most important components of the system is the occupancy sensor, which is able to tell on which section there are trains. As I mentioned, each turnout is responsible for controlling the sections that are connected to it. And to each turnout, there is a microcontroller attached on which our supervision software is running. We use BeagleBone microcontrollers in this project. If a train would collide into each other, then before the accident happens, we stop them by the actuators, which are attached to each section, and the actuators are sending the stop and the go signals to the trains. Since it is an online presentation, during the talk there will be several screenshots about the system and about the physical layout of the track, with some decorations on the table and with some trains moving around. After the physical overview, let's have a look at the software side, at the logical structure. We developed a two-layer, double-layer safety logic in order to supervise and to prevent the trains from colliding. The first layer consists of a distributed state machine. As I mentioned previously, each turnout has a microcontroller which is responsible for controlling the sections that are connected to this turnout. To these microcontrollers, we deployed distributed state machines, which were developed in the Yakindu state chart tools. We modeled every concept in the system, so the sections, the turnouts, and the trains, into state machines. The state machines are able to send signals to each other, and based on these signals and based on the safety logic we modeled in the state machines, the turnouts are able to communicate with each other via network messages and decide where the trains are moving and which trains would collide. And before they would collide, they are sending out the stop signals to the corresponding trains to stop them. From these high-level state machines, we generated code using the Yakindu state chart tools, and we deployed these generated codes, these generated state machines to the microcontrollers on the system. And another benefit of using this model-based technique was we could automatically derive formal models from the high-level state charts. And based on these formal models, more specifically timed automata, we could run different formal expressions to check if the models are correct and to prove that they are stopping the trains before in every dangerous situation before any accident could happen, so that we could also attach a formal proof to the correctness of our distributed safety logic. That was one layer of safety that we implemented. Another layer was based on computer vision. To each locomotive, we attached a marker. Based on the movement of the markers, we could decide where the trains are moving and which sections will be occupied. And from these coordinates and these marker information, we implemented a graph model in memory, which is processed by the Viatra model query and transformation framework. We developed high-level events and complex events in the WEPL language. For example, we modeled how it looks on the how it looks in a graph when two sections are occupied and when trains are moving certain directions. And from these graph patterns, we modeled how dangerous situations look like. If these dangerous patterns appear in the model, so in this graph model in the memory, then the patterns will have match. And if those matches appear, then we stop the trains which caused these dangerous situations so that they cannot collide into each other. And these two layers, these two safety layers are independent from each other. And if any of them sends out the stop signal, then the corresponding trains will be stopped. We presented our work on several occasions, on several events where both students and children and their parents attended. Our main targets were the Researchers' Night, because that's where primary and secondary year students go, and also their parents go there who have some interest in science and see interesting presentations. Other events were the university days, where the primary audience were students, and open lab days, and we attended these events between 2014 and 17. And in 2016, we participated in the Open IoT Challenge. The goal of this challenge was to combine different open source IoT technologies to prove their capabilities and also to create very interesting demonstrators. And we were lucky to win the third prize on this competition. And in the following year, in 2017, we presented our work on the EclipseCon in Ludwigsburg. The participants of the conference could control the trains remotely, and our safety logic was running in Budapest and was stopping the trains before any dangerous situations could have happened. Let's see some pictures from these events. As I mentioned previously, at the Researchers' Night, the target audience were children or primary and secondary year old students. And on these events, we brought the model railway track. We got several displays on which we could explain what is going on the track. And the participants of the events could control the track using the remote controller, and our supervision system watched the track and follow the trains before they would before any accidents could have happened. And there are some more there are some more pictures about these events with some more decorations on the track. And as I mentioned, besides Researchers' Night, we also attended University Days, where the target audience were university students or secondary school students, their parents, or interested researchers, and so on. So for University Day, it was a broader audience. And let's see how we won children's heart for model-driven engineering. Well, the secret ingredient of the track was basically the trains were transferring several sweets and gummy bears or other kinds of sweets. And if the locomotives stopped in front of the children, then they were free to take as many sweets as they wanted. And besides these events, we had several other publications. In 2018, we published a paper at the NASA Formal Methods Conference, where we provided an overview of the track. We explained the different IoT technologies that we applied, and also the two layers of the safety logic. These two layers were presented in separate research papers as well. In 2015, we presented the graph model-based supervision system, and in 2014, we presented the distributed state machines. There we have a YouTube playlist where you can watch several videos about the track, a promotional video, and also a video about the everyday life of the trains on the track. So how they are moving and when they are stopping and so on. And finally, I would like to thank all my former colleagues, student colleagues, without whom we couldn't have built this track. And we would like to also thank for all the supervisors who gave us guidance and also supported us through this journey to build the track and also to build the software, correct it, and without them we couldn't have participated in these events. So I would like to thank everyone who was involved in this project. And finally, without our sponsors, we couldn't have attended this project. So I would like to thank the companies, the research groups, the people involved in it, and also some other sponsors who provided us help or support through this project. And if you would like to read more about the project, then you can visit the project website, or you can visit the website of the research group, write an email to the leader of the research group, or if you have any questions, then you can also contact me. And thank you for your attention, and please let me know if you have any questions.